Hello, everybody. Thank you for joining the AAA Bronx chapter. My name is Bill Caplan, and I'm a member of that Bronx chapter of the AIA. This morning we have a 1 CEU presentation, Reducing Embodied Carbon to Reduce Global Warming. Please note that this session is being recorded, and we ask you to please turn off your microphones until the Q&A session at the end. For chat box questions, please address them to everyone. And Bob Esnard will try to ask them for you. I hope, Bob, I don't know if you're here, if time allows at the end. Before we begin, I'd like to thank Bob Esnard, the backbone of the Bronx chapter, whose idea it was to sponsor this course. Excuse me one second, I got a problem here. A little technical glitch. Okay. Bob, it was Bob's idea to sponsor this course, and he did the work to get it accredited. A course which may become a series on architecture and climate change. And a big thank you to the Westchester Hudson Valley chapter and your executive director, Valerie Brown, for providing your Zoom platform. I would like to encourage all of you.
This is the base of the building.
Somebody has their microphone on, if they could. Got it, thank you. I would like to encourage all of you to join the AIA Committee on the Environment, whose 12,800 members keep alive the discussion of sustainable design. So let's begin. This course was derived from my recent book, Thwart Climate Change Now, Reducing Embodied Carbon Brick by Brick. It was published by the Environmental Law Institute in 2021. While researching the relationship between the built environment and global warming for more than a decade, I've uncovered some unsettling things. One was that global warming is increasing at an alarming rate, something more obvious today than it was back then. Another thing that became apparent was sustainable design's singular focus on saving energy, which often takes embodied carbon for granted. I will elaborate on that in the second learning objective. Given the massive impact of fossil fuel energy on global warming, you may be thinking, what difference does your work make? Perhaps this next slide will give you a clue. Nearly 40% of all energy-related emissions worldwide arise from the construction and operation of buildings. Every one of you can help cut that back. The built environment is our largest source of energy-related climate-changing emissions. Consequences from what we build today, from your next project, will persist for the next 50 to 100 years or more. But most unsettling of what I learned was how little time we have left to come anywhere near capping global warming to the Paris Agreement goals, to the 1.5 to 2 degrees Celsius. And therefore, how little time we have left to reduce our carbon emissions, which means we must start to reduce them now in 2022 and not wait until the 2030s. The first objective of this course is to clarify that urgency, to explain why we need to reduce emissions immediately. After all, some countries have pledged to be net zero as early as 2050, and there are multiple pathways to achieve the Paris Agreement targets. So what's the rush? That depends on the answer to two questions. The first, how many more tons of carbon emissions can we continue to emit? The second, before warming gets out of hand. The second, what is the status of our decarbonization? Let's cut to the chase and see where we stand. Although temperatures stayed within a plus or minus quarter degree bandwidth for the 2,000 years prior to 1900, since 1900, they have increased more than 1 degree C. Notice the sharp rise since 1970, followed by nearly a half a degree rise from 2000 to 2020. This temperature increase comes from the increasing concentration of carbon dioxide in our atmosphere, atmospheric carbon. In the early 1900s, for the first time in over 300,000 years, the concentration of atmospheric carbon exceeded 300 parts per million, that's ppm. Here we are 200 years later, and atmospheric carbon has increased by 38%, reaching 420 parts per million. In the 100 years prior to 1722, the increase was minuscule, just 2 parts per million. That was followed by a mere 7 through 1822. There was a slight uptick in the late 1800s after the Industrial Revolution, adding a total of 20 parts per million through 1922. But then it accelerated, increasing 116 parts per million, reaching 420 last month. 100 of those 116 parts per million were added in just the last 60 years, at a rate we now know to be alarming. And with it, global warming followed suit, which we now know was its effect. Temperature increases are nearly linear with the increase of atmospheric carbon. Every ton of CO2 emissions adds to global warming. Here's how. Greenhouse gases regulate the Earth's temperature by absorbing some of its infrared heat energy and then re-emitting part of it. This warms both the atmosphere and the surface. To maintain a temperature range fit for human survival, constancy is crucial. Water vapor is also a greenhouse gas. Combined with stratiform clouds, water vapor and clouds contribute nearly 3/4 of the heat re-radiation, contributing 3/4 of the greenhouse effect. Carbon dioxide is just 20% of the greenhouse gas mix, but its enduring presence influences air temperature, and air temperature influences the air's moisture content from the water vapor. Changes in atmospheric temperature and pressure cause water vapor and clouds to precipitate rain, sleet, and snow. This removes wet water vapor from the atmosphere. But unlike water vapor, CO2 neither condenses nor precipitates from the atmosphere. If the concentration of CO2 falls, the atmosphere cools. This causes water vapor to condense, to precipitate out of the atmosphere. But when the CO2 concentration rises, the atmosphere warms. This causes water to evaporate from the Earth's surface. Those vapors amplify the greenhouse effect and warm the planet. Though CO2 is only 20% of the mix, by regulating the atmosphere's water vapor content, its greenhousing effect amounts to 80%. What we spew into the atmosphere today and tomorrow will increase global warming immediately. It will stay there for hundreds of years, if not a millennium. So how many tons of carbon can we continue to emit before the warming gets out of hand? And how many tons per year are we emitting now? The answers can be found in these two reports, Climate Change 2021 from the IPCC and the Emissions Gap Report from the UN Environment Program. The emissions allowable to stay within 1.5 to 2 degree targets can be found in Climate Change 2021. Let's take a look. This table addresses the remaining carbon budgets, the volume of carbon emissions allowable until net zero is achieved. Net zero means that carbon emissions can be no higher than the amount of carbon freed from the atmosphere. Calculating from the beginning of 2020, each emissions allocation here is tabulated with its likelihood for success from 17 to 83%. Given the consequences of continued warming, an 83% shot is the minimum we should shoot for. Would you bet the planet on anything less? to hold warming to 1.5 degrees with 83% probability allows for 300 gigatons of additional CO2 emissions. Now that's cumulative from the beginning of 2020, 300 billion metric tons until we achieve net zero. Defaulting to the 2-degree target, we can triple that to 900 billion metric tons. That sounds like a big number, but how much do we actually emit each year? This is a graph of our annual CO2 emissions, the basis for calculating the carbon budget. Fossil CO2 emissions, bright purple, make up the bulk. The rest are from land use. Their total has exceeded 40 gigatons per year for nearly a decade. If we at least maintain this range, what's the prognosis? At 40 gigatons per year, we will exceed the remaining 300 gigaton budget for 1.5 degrees C in 2027, only 5 years from now. And with it, our 80% chance of success. We will exceed the 900 gigaton budget for 2 degrees in 2042. Yet net zero targets for the world's largest emitters are 2050, 60, and 70 at best. For any reasonable shot at capping warming to 2 degrees C or less, significant reductions are required over the next 5 to 10 years. So what is the status of decarbonizing our energy supply? By generating energy from carbon-free renewables. Total carbon-free energy in the United States in 2019 constituted 14.9% of total energy consumption. But 57% of that was from nuclear. Carbon-free renewables constituted a mere 6.4% of total US energy consumption. We can't wait for the promise of carbon-free energy in the future for wishful thinking. We need to start cutting carbon now, which brings us to learning objective number 2. What is the relationship between a building's embodied carbon and operating emissions? And what is their respective relationships to global warming? Because operating emissions from energy use recur throughout a building's lifetime, operating energy is usually the earmark for sustainability, for reducing carbon emissions. Regardless of a building's inherent design efficiency, the installation of energy-efficient heating, cooling, lighting, and equipment will reduce energy consumption and thereby reduce operating emissions. But energy-efficient appliances and equipment are the low-hanging fruit, merely a function of budget and availability. This is not particularly taxing to an architect's design. Designing energy-efficient buildings or retrofits is a more difficult task. It is an art form that requires engineering finesse. But these solutions by themselves address only half the equation. They only address operating emissions. They ignore their own carbon footprint, the emissions generated while fabricating the materials and the equipment, as well as those generated by constructing buildings and infrastructure. These are the embodied emissions. So how do these two sources of carbon emissions, embodied and operating, relate to each other? That's simple. First, you mine, harvest, process, manufacture, transport, and assemble or construct. Then you get to use it. Embodied emissions are up front. Operating emissions come later over time. Unfortunately, embodied emissions are released way before any product is purchased, before any building is occupied, before any infrastructure is even used. They accelerate warming in real time, way before any benefits from operating efficiencies can even begin to accumulate. It can take a decade or more of operating emissions to merely offset their upfront embodied emissions. Let's look at how both embodied and operating emissions accumulate over a 10-year period. As this graph indicates, over the next 5 years, 70% of the carbon emitted from new buildings will be embodied emissions. 10 years out, embodied emissions will still be the greatest share, equating to 60% of the total. Embodied emissions are the first tally of sustainability. Operating emissions are the second part of the equation. Operating savings can depend on the weather, the economy, good practices, or the occupant's functional choices. They can also be improved upon in future years. But this is not so with embodied emissions, which are locked in up front, already released. They accelerate global warming in real time, way before benefits from energy efficiencies accumulate. Already emitted, they cannot be mitigated. The good news is that we can start reducing new embodied emissions immediately by choosing low carbon materials and low carbon solutions for the next project we design. Unfortunately, making a correct choice is not always as obvious as one may think, even with the tools that we have, which brings us to learning objective number 3, understanding why materials databases and compilation tools are difficult to use and need more development. Databases typically list materials by their emissions per unit of mass. They are listed here with the highest emissions per unit of mass at the top, to the lowest, the best, relatively speaking, at the bottom. This yields some surprising results. Aluminum is the worst, concrete the best, cement and glass are in the middle. Given the high temperature necessary to process aluminum, that seems understandable. So should we use concrete over steel, ceramic tile over vinyl cladding? But this ranking is solely determined by mass, by the pound or the kilogram of each material. In actual use, the amount of a material used varies widely by its use in construction or as a component of a product or an assembly. For example, a concrete structure requires the use of a lot more concrete to support a given load than a steel structure requires of steel. So even though a pound of steel released more embodied emissions than a pound of concrete, for structural use, steel is the best choice. For cladding, aluminum or vinyl products could be better choices than brick or better than some composite products. It depends on a product's composition and its thickness. It comes down to processing temperature, how much it is used in a specific product or application, and let's not forget its transportation, how far it is traveled, where it's coming from. I bring that up because this Miami high-rise was clad with 4,800 precast concrete panels, weighing up to a ton or more each. They were shipped all the way from Dubai, over 9,000 nautical miles. Processing temperature is also relevant. For example, firing ceramic, porcelain, and brick, sometimes multiple times for surface effects, like glazing the surface, or refiring to create a color or a shade of black. High temperature manufacturing and processing mean the high energy use, which releases a high level of embodied emissions. To sort all this out, architects, designers, and engineers need help. We need a simple way to compare products to enable appropriate choices. Environmental product declarations, EPDs, are the closest things we have to aid our selection. But in their current form and limited availability, we are still very much on our own. Let's take a look at EPDs. EPDs will eventually provide data that is useful for quick emissions comparisons in a simple, easy-to-use format. And they will be available for enough specific products by model number to make a difference. But at the moment, they are far from useful for a simple upfront evaluation of material and product choices. Upfront is the key word here. Doing an embodied carbon analysis on a completed project is too late. too late to make a difference. Low carbon choices must be part of the design process. Not enough manufacturers offer EPDs. And for those that do, there is no single standard for evaluation. This makes comparison difficult at best. Some EPDs simply provide generic data, a hypothetical average for an industry-wide product, where products from different manufacturers can vary widely, such as for vinyl siding, as with this EPD for the industry average. The most useful EPDs are provided by a manufacturer for a specific product. But even there, while some EPDs are externally verified to specific standards, those standards vary on a global scale. Others may be just internally reviewed. But in all cases, it's the manufacturer that decides which categories of the life cycle analysis will be included in the EPD's emissions calculations. Let's take a look at this EPD for vinyl siding. The EPD contains 12 pages. Some have as many as 15, perhaps more. The top box here is extracted from page 3 of 12. It informs us that this EPD is for an industry-wide average of 0.04 inch thickness vinyl siding with a 50-50 ratio of PVC and ASA, whatever that is. Table 3 in the box below from page 7 lays out which parts of the life cycle analysis the manufacturer chose to include, which is indicated with an X. In this case, it's all of them, from A1 through C4, from raw materials extraction to disposal. All of the emissions from cradle to grave are part of a product's embodied carbon. But given our urgent need to cut emissions now, the upfront emissions, those from material extraction through manufacturing and installation, matter most. The magnitude of those emissions are located in the global warming potential data line in blocks A1 through A5 on its page 9 shown here. And it's highlighted with a red border. The emissions are expressed in kilograms of CO2 equivalent gases per 100 square feet of industry average vinyl siding. We'll just add up the numbers in A1 through A5, and you'll have their total embodied emissions to compare. Perhaps expressing the numbers in this scientific notation, E plus O1, etc., makes the interpretation a bit confusing. I think you get the point. This EPD is for a specific model of carpet tile. It's a bit easier to read, especially when you know where to look. If we are looking to compare upfront embodied emissions, we could ignore most of its 15 pages. Page 10 has a clear presentation of the life cycle info, columns A1 through A5 here, providing a clear statement of the upfront emissions from raw materials through installation. They add up to a little over 7 kilograms of CO2 per square meter, which is plainly visible. The only inconvenience is that the unit of reference, the 1 meter square, was indicated on pages 5 and 6, not here on page 10, where it's needed. Nonetheless, this EPD provides an easy-to-read presentation. Although EPDs have a role in providing this much-needed information, what we need now is a simple compendium, a list of upfront embodied emissions by product, manufacturer, and model number. A simple database for architects, designers, and engineers, for a common sample size computed with standard rules. We also need user-friendly software to compute entire assemblies, for sections, floor plans, and elevations, and for interior fittings as well. If we can compare the emissions from a material A to a material B, even generically, or better yet, from one manufacturer's product A to another's product B, we can cut millions of tons of carbon emissions quite quickly. Why? Because there are more than 119,000 registered architects in the US alone, Worldwide, the number is estimated at 1.3 million architects, and that doesn't include interns. That's a lot of specification power. So how can we reduce embodied carbon now significantly while we await for more user-friendly tools? This is learning objective number 4. Let's start with concrete. Concrete is the most used building material on the planet. Twice as much concrete is used in construction as all other building materials combined. If you read Architect magazine, the journal of the American Institute of Architects, you might have seen this ad. It ran in an issue featuring an article on decarbonization. The ad was placed by Build with Strength, a coalition of the National Ready Mixed Concrete Association. Per the ad, the coalition consists of civic organizations, fire safety professionals, architects, engineers, and industry experts. That sounds pretty impressive. The headline reads, "What building material absorbs carbon for the entire lifespan of the building? Concrete is the answer." True. But no, regardless of this claim, I am not proposing that we choose more concrete. Exposed concrete surfaces do absorb carbon dioxide slowly over time. Well, so do some rocks, and so does soil. But the decades required for meaningful absorption nowhere near compensate for the enormous emissions spewed daily by cement manufacturing. No, concrete is not the answer to stave off carbon emissions, though someone reading this advertisement in Architect might be influenced to believe so. Concrete itself is not the problem. It's the binder that secures the mix, the cement. More than 4 billion metric tons of cement were produced in 2020 alone, spewing 2 billion metric tons of CO2 to the atmosphere. Half of cement's emissions are a chemical byproduct from breaking down limestone at 1400 degrees Celsius. It's a reaction that releases CO2. Here's the worst part. Only 40% of cement's emissions result from burning fossil fuels. Only those emissions can be eliminated by fuel source decarbonization. Less than half of cement's emissions. Cement concrete is also used to fabricate a large array of products, not just for construction. From ornamental flower pots, garden sculptures, and furniture, to building ornamentation, roof tiles, facade panels, and institutional interiors. Concrete is an architectural style in itself, even for buildings touted as sustainably designed. Cement manufacturing, one building material alone, is responsible for 7 to 8% of the world's energy-related carbon emissions. Reducing the annual use of cement by just 15% will eliminate more than 300 million metric tons of CO2 per year. That's approximately 1 billion metric tons every 3 years, 1 gigaton. This is a building on, This is a building on William Street in New York City's financial district, completed in 2020. A 66-story, 800-foot tall residential tower with a curtain wall facade. The entire building is clad with hand-cast concrete panels. The fact that concrete is a component of this building is not the issue. Rather, it's the overabundance. This massive use of concrete has emitted significant embodied emissions just for an aesthetic statement. This is gratuitous carbon. An abundance of concrete should be neither a teaching tool nor a design aesthetic to emulate. There are many lower carbon means to effectuate a design statement. But it's not always concrete. The excessive use of other high embodied carbon materials in the name of aesthetics or in the name of sustainability is also a common problem. This is Gates Hall at Cornell University. A computer science building opened in 2015. It's LEED Gold certified and is touted to have state-of-the-art sustainability. One goal was to establish a consistent level of daylighting while reducing the need for cooling, to be accomplished with exterior steel screens oriented to cut heat loads and glare. As applied here, we have a perfect example of competing design goals. I'm referring to aesthetics versus true sustainability, which must account for its own carbon footprint. You're looking at the building's north facade, where solar shades serve no real purpose, situated on the north side of a building. Viewed here from the inside looking north, with no useful purpose, these screens are merely an aesthetic appendage, one that adds to the building's carbon footprint, adding to its embodied carbon. Aesthetics here is trumping sustainability, which is sustainably negative. One can even question the efficacy of these solar shades. This is an interior view south. On my visit, the sun was so bright, it was hard to see one's computer screen. It was also hot. Notice that all of the interior shades were pulled down to shade the solar shades. From my point of view, this is gratuitous green. Excess embodied emissions for aesthetic purposes is a problem that is easy to solve. This is true for buildings both big and small. It only requires a consciousness of embodied carbon. But let's not forget there is a silver bullet, and it's called wood. Please use it whenever you can. Wood sequesters CO2. During growth, 1 pound of wood absorbed 1.5 pounds of CO2 from the atmosphere. Dressing a pound of wood for lumber emits roughly half a pound of CO2. Therefore, wood building products have a net benefit, sequestering 1 pound of CO2 per pound of lumber. This building in Norway, standing 280 feet tall, is 18 stories, completely constructed from wood. It was completed in 2019. It's mixed use, housing a hotel, a restaurant, offices, apartments, and a swimming pool. Glulam was used for columns, beams, and trusses. Cross-laminated timber was used for walls bearing secondary loads, including elevator shafts and stairwells. But it's not just large-scale projects that matter. Small projects from a back porch to an office renovation matter as well. And here's why. Cutting embodied carbon is directly tied to market demand in a very big way. Materials and products are manufactured in large lots. Their resupply for stock is subject to demand. The accumulation of small orders drives suppliers to reorder, which drives new manufacturing in large quantity. It's not a particular singular purchase that reduces emissions. It's the mushroom cloud of carbon emissions from each stage of a large lot production. Production initiated to meet specifiers' demands, both large and small. If demand falls for a particular product, so will its remanufacture. But life is never simple. Looking up a particular material's emissions per unit of mass is difficult enough. It can also be misleading. The average thickness for vinyl siding in that EPD I showed before was 0.04 inches. Yet some brand name models are 0.05 inches. This difference may seem innocuous, but it adds 25% more mass, thereby releasing 25% more embodied emissions. Even materials with a high carbon footprint can be preferable in multi-material products if the total mass they add is small. The use of aluminum often fits in this category. When you consider a wall's construction, including its fenestration, there are numerous pieces to the puzzle, numerous material choices. Brick, especially glazed brick, may be high in carbon, but how about a thin brick veneer? Is brick over concrete masonry okay? What about interior floors and wall treatments? These are the problems you all have to deal with, and this is where we lack the tools. the tools that can help us choose low carbon selections. There is an interesting tool online that I've discovered that can help you compare embodied carbon content for various material assemblies. It's called Kaleidoscope. It's being developed by Payette, and it's currently set up for envelope and flooring systems. Let's take a look. This is a partial screenshot of the flooring systems page with all its options active. The bar graphs indicate each assembly's global warming potential, the GWP. This is expressed in kilograms of CO2 emissions per square foot of assembly. Notice the blue bars on the bottom. These are negative, meaning that these assemblies sequester CO2. This group is for various types of wood. What's nice about this is that if you move your cursor over a bar, for a particular assembly type, the assembly's details are revealed. This one is for porcelain ceramic tile with cement grout and thin-set mortar. Its emissions are 1.12 kilograms of CO2 per square foot. I've chosen a few of these screenshots randomly just to give you an idea of how this works. This is solid vinyl flooring with a vapor barrier over a cementitious layer. And at 1.21 kilograms of CO2, it's about 8% higher than the porcelain, I suspect due to the underlayer. This one is for a thin-set epoxy terrazzo, 33% more emissions than the porcelain tile. And here is one for a low-pile nylon carpet tile with an underlayer similar to the vinyl. Its emissions are in between the vinyl and the porcelain. And then we get down to the wood group. This one is engineered hardwood veneer flooring laid over a vapor barrier and a plywood substrate. Its net carbon is negative, a minus 0.79 kilograms of CO2 per square foot. And the last one I have here is, this is solid hardwood planking, mounted the same way as the engineered wood, with it's more than 3 times better than the engineered wood. Although all of these examples are modeled for a genetic flooring material without reference to a specific composition or thickness, and for generic mounting and installation, you can still easily discern their dramatic difference in emissions from one genre to another. Kaleidoscope even provides a handy calculator. It lets you compare the different options and do it for a floor area of your choice. I've done it here for 100 square feet and using concrete and comparing it with terrazzo, vinyl, low-pile carpet, and both engineered and hardwood plank. And so you can also add various other options. This is a screenshot for the envelope assembly section for a buildup of thin-set thin brick with mortar on a cement board backer with mineral wool insulation. It works the same way as the flooring page. And here too, it has a comparative calculator. I set it here to compare a 4-inch granite veneer against insulated metal panels, aluminum spandrels, precast concrete panels, brick, and thin brick veneers. You can access Payette's embodied carbon calculator at payette.com/kaleidoscope. And no, I don't have any relationship with Payette. It needs a lot more development to enable us to offer the best low carbon alternatives to our clients. Nonetheless, exploring the existing database with its tools will give you a heads up on how to approach low carbon choices. The most important thing that all of us can do now is to start making more low carbon choices, to do it immediately. We are on a tight timeline, and the next 5 years is very significant. Reducing the buildup of embodied carbon at this moment is essential. Think of the next 10 years as a special carve-out, an exception. Think of it as our temporary vaccine against climate change. until hopefully we progress toward more zero carbon energy. Making a dent in carbon emissions over the next 10 years requires us to take action over the next 5. I urge you to do so. Thank you for listening, and I'll be happy now to address any questions. Okay, I'm unmuted. Okay, so okay, anybody have any questions to ask? Anything in the chat room? If you do, please unmute your mic.
I have a question, Bill.
Yes, Julian.
I noticed that with the wood product reduces the carbon quite a bit. But things like if I use wood plank on an exterior for a house, what happens over time when you are using paint on it? Does that reduce the carbon benefit? And also, if I got to keep painting over time, does that also really cause a detriment over the long run where something would end up being kind of balanced out compared to other products like vinyl, where you have an upfront one-time hit, but then you're not really doing any maintenance after that?
Well, that's a really good question. In fact, I usually get that thrown out at me when I do these things by people who are promoting vinyl. So, so the answer to that is, first of all, wood siding lasts a long time, and 15, 20 years, and if it's properly taken care of, and clearly, if you paint on top of with appropriate paint or any coating, you're also giving it protection. Now, it's true that the paint itself has a carbon footprint, but it's nowhere near in any level of consideration compared what the wood is saving, or what especially compared to vinyl. So that is general category number one. So you're much better off by tons of CO2 emissions in the wood. And so clearly, if you're in an environment where wood rots a lot, then that's out the window. But I'm excluding that. But the second thing is, and it's something that it's very difficult to face, is this timeline. I mean, seriously, we're looking at a 10 to 15 year period. And if we don't cut emissions now, there's no way on earth that we're going to be able to even hold 3 degrees centigrade. So that's why I talk about talking about a carve out. I mean, we really need to do what we can, looking at this next 10, 15 years period. And now, if in fact some of these gains are really made in reducing embodied carbon in our power supply, then that eases up on things, because eventually when everything is made by zero carbon power, then it doesn't make a difference anymore. Use all the energy you want. But the reality is then it's not going to happen for another 30, 40, 50 years. So so that it's when you just look at that number of that you're sequestering at least 1 pound of CO2 per pound of final wood that you use, compared to emitting pounds of CO2 for any other product. I mean, hands down, wood is the answer.
Okay.
I have a question, if I could.
Yes, Bob.
I just wanted to know, for me, it was a wonderful presentation and very eye-opening for me. I've never really paid much attention to this, only saw it in the most general way. Has there been any legislative help in this direction? Because it seems everything is the lead, everything is sort of more related, as you described, to the fixtures or the operational side of the equation of this issue. Is there anybody considering this, or is there some group we should be all talking about this a little bit more than just architects? We're just architects, but we're architects that don't control everything. And I was just curious if you had any suggestions about how to, make this issue more of a bigger issue.
Yes, I mean, thanks, Bob, for bringing that up. I mean, actually, there is a movement, a big movement now to start doing this. And there are, I believe, 6 or 7 states who are in the process of instituting or starting to institute embodied carbon limits on future building construction. In fact, I think in Vancouver, the city of Vancouver in Canada, they are already halfway through this. I mean, the first step is for them to earmark, what is an appropriate amount of what's the average embodied carbon in buildings, for larger buildings to start with. And then in a few years, they're going to change the building codes. Now, in New York City, we already have local law 97, which as of, I think, 2024, is going to limit the amount of operating emissions per square foot in, I think, buildings over 25,000 square feet. And so we are pushing now to have added to that embodied carbon. Now, I think in New Jersey, they're already, I think, starting legislation to legislate the use of low carbon concrete, low carbon concrete, not using Portland cement. And the problem is, I mean, there is low carbon concrete available using different binders. The problem is that it doesn't have the strength that you need for construction loads. Also, anybody interested in this, a good place to look is if you go online, the Carbon Leadership Forum. I think it's clf.org. Their sole purpose is to deal with eliminating carbon emissions, and they are working with various states and offering solutions to help with this.
Terrific, thanks.
Bill, I have a question.
Yes.
When we were designing way back, the life of the building was like, 20 years, 30 years. But when you start doing like the public realm buildings, we want those buildings to be there for a very long time. So my question is like, if you're going to be using wood or any other materials other than what we used to do, like concrete and stone for large public buildings, because they want them to be there forever, then having to replace some of the materials like wood again and again and again to get the 100-year or 150-year or whatever life of the building, would we not be using again and get more embodied carbon in the materials to replace old worn out material while the stone will be there for a very long time?
Well, okay, I think you're maybe talking about the exterior. I mean, interior wood is, and you go into Europe, you'll see wood that's 1,000 years old on the interior. But even exterior, I mean, if it's properly taken care of and maintained on the outside, it has an extremely long life. Now, but it's not just, again, this is only the first section in my book. I cover a lot of different areas of reducing emissions. But even in the case where you're going to use normal construction materials or wood or stone or metals on the outside of a building, the methodology of construction also is significant. But also, I mean, if you look at, if you compare, primarily concrete structure buildings to steel structure buildings to the combination of concrete and steel, the worst is concrete. And if you go to concrete and steel, there's a huge benefit in savings. And if you go to steel construction, it's even better. And then if you're using steel, well, most steel today for structural, I think maybe in the States, uses a high level of recycled steel, 80 or 85%. So there's a lot more to it than just saying it's wood or not wood. Also, and it's in my book, there's some papers that have been written that the structural methodology used for tall buildings, and plus in New York, in other cities that's very relevant, is very significant. That depending upon the height of the building, that if you take the 3 standard ways guiding for all the way up to super tall, that there's a peak period of height, which is preferable versus carbon emissions. So there are some structural technologies that are used, that are, maybe great at 40 to 60 stories. But above that or below that, there are more carbon footprint per square foot, and it's better not to do that. So there are many different techniques other than just saying, don't use cement or use wood.
Thank you.
Anybody else? I'm just scanning the chat room here.
You have one question, Bill,
Yeah.
for somebody does to have a mic. The question is, can you name a few of the other materials tools for carbon use, and if any of them are as useful? I guess he's talking about the chart you had when you talked about how you can evaluate, what you're doing.
Right. So I'm sorry to say no. Yeah, I've looked at a lot of them. And look, I'm an engineer, so I have a materials engineering degree, and I'm coming from the world of engineering. And I, every time I look at these tools, I say to myself, my God, well, sure, if you work for a large firm that's got, engineers on the staff and people dedicated just doing this, fine, you can crunch through the numbers. But I can't find anything that's really, simple to use up front to make, simple decisions, even for just interior design. And so, which is why I selected, I found this Kaleidoscope. Actually, I found it on this Carbon Leadership Forum. In fact, which leads me to a question. There's a question in the chat box. It says, in Kaleidoscope, why are granite and slate so high when compared to porcelain? That threw me as well when I looked at it. But I spent a lot of time trying to ignore it, but I couldn't. So I dug into it. And so the problem is what you're looking at is a specific assembly that they chose to be generic for their example. So you're looking at, I think it's a 4-inch thick slab of granite. Now, first of all, I guess probably the emissions are high from polishing the granite in the first place. But that's being compared with a porcelain tile, which I would normally recommend people not to use because it's got such high emissions to make it. However, it's in a very thin section, and then it's not the tile alone; it's this assembly of the tile, on a cement background, or I forget exactly how they have it. So so that's why there's problems with this in using Kaleidoscope itself. But when you look at it and start to play with it, which is what I did, you start to get a sense of, okay, where the problems are, and what kind of choices you can make to start cutting things. Anybody else? I'm just scanning down this.
Yeah, I have a question.
Yes, John.
Thanks. Thanks for the presentation. It was really great.
Thank you.
I was wondering, when we talk about the kind of balance between embodied carbon and operational carbon, have you noticed anything that like might guide us toward, for instance, a higher embodied carbon number, but with the anticipation of lowering embodied or operational carbon? I'm thinking of like triple pane windows, you know, have a bigger embodied carbon hit, but that would lower your heating and cooling, or more concrete for kind of thermal mass and thermal warming to lower operational carbon. Is there any work being done on that, or research that you've seen or been excited about?
Okay, well, is your question, you're asking me where that borderline between embodied and operating? I think,
Yeah.
okay, so an example, you know, a thing that really comes to mind is, you know, is insulation, which is interesting because, you know, one of the key ways to help get a net zero building, you know, is to pack it up with insulation. Well, but the fact is, you get to a point where you have the insulation starts reducing the benefit for the added insulation. And depending upon the kind of insulation that you're using, it can really have a negative effect, because insulation itself, you know, has embodied carbon. And so, you know, the whole concept of thinking of the amount of material you use is really, you know, the best way to start. And you know, just the more material you use, no matter what it is, then, and I guess instead of wood, then the more embodied carbon you're going to use, put into the building. You know, and the benefits of most of the benefits, when you really dig into the numbers that are coming from the efficiency of buildings, have absolutely nothing to do with how architects built the building. And when you go back and look at a lot of the numbers that have been put out, patting, you know, ourselves on the back for the great job we did over the last 15 years. When you look at the numbers, you know where it's coming from? A lot of it's coming from switching to first to the switching light bulbs and eventually getting to the LEDs. I mean, like a third of the savings was coming from that. And then a lot of the savings came from the weather cycle, where there was less air conditioning or heating in the weather coming. And so very little of it could be tied to the actual benefit from building constructions, or it was coming from using, installing more efficient appliances. And again, that's why I point out none of this has to do with your design of a building. So, now when you get out of a city where you're regulated to the street design, where you have to, street is oriented one way or the other, where you can start orienting buildings better for, sun or shade or pick up heat, and et cetera, in the winter. I mean, all of that makes a difference. It's the same with solar panels. I mean, in the northern, and again, I cover all this in the book in detail, in northern climes in this country and all around the world, most of the solar panels that are installed on residential buildings are, it's taking 8, 10, or 12 years or more just to equal the embodied carbon to make the solar panel. And that's if they were 100% effective. But a good portion of those are in the shade. So if you have an existing home and the roof is slanted, so it's facing, the slant is facing east, or even west, and that's how you put your solar panels, you're not going to get enough in the north, enough output to pay for the embodied carbon in probably 15 years. So, then there's the argument, well, we need to make that investment. Well, making that investment now is a negative thing, because we're in this 10-year period that we need to cut. So I'm not saying don't put solar panels on the roof of a house, But I'm saying in the northern climes, unless you have a perfect orientation, wait 5, 8, 10 years. There's plenty of places in the country, all the rest of the country, where it makes a difference. And of course, solar farms, no matter where they are great, even if they are in the northern climes, because the money is spent to buy extremely high efficiency panels. They're oriented exactly in the right direction. They are being maintained and cleaned. So it's a matter of just using our common sense rather than saying, well, this feature is a sustainable design feature. Well, it is in certain cases, but not all of them. I hope that answers your question. Somebody just asked, is building reuse a much better alternative? Oh, absolutely. Yes, no question about it. So, and some of them retrofits are too. An exemplary one is actually the Empire State Building in New York City. I don't have the numbers in front of me, but they, rather than replacing all of the windows in the building with new windows, they removed all the windows and rebuilt them on site with double pane windows, but putting in an insert in the center, which is a energy blocker, and various other things that were done inside the building, all focusing on cutting embodied carbon while they were looking for efficiency in operating carbon. And so they got both. Anybody else want to ask anything? I think, okay, well, I thank you all. Wait a minute, just hang on a minute. I got another question here if you want to stay in. Okay, there's one question about the Penn Station in New York. How do you reconcile tearing down these buildings? And actually, they're adding an enormous amount of embodied carbon. And if you go online, if you go onto the AIA, on your AIA account, and look at in the Committee on the Design, I wrote a piece on, committee, I think it's both on design and also on the environment. I wrote a piece on that discussing the issue with the Penn Station, the new renovation plan. It's a bad one as far as embodied carbon goes. And there's one question here about ask me about a system. Do I have a favorite system for sustainable design that architects can steer projects towards, given that LEED and BREEAM don't always align points with embodied carbon? Again, it's lacking, and I would hope that pressure would be put on LEED and BREEAM to start making embodied carbon a significant part of qualifying for design. I mean, we all know that LEED in specific does not have negative points. So, I mean, you could end up being LEED gold or even LEED platinum and be polluting at the same time. So LEED really serves a purpose. I hold it in high regard for educating so many people on what we need to do, but it's not a standard to hold up and say, well, okay, even I'm LEED platinum, and therefore I've done my job. It doesn't really mean that. So I think, we're still all on our own. And boy, it really adds up when you just start to apply it in everything you do. There's just no question it's going to make a difference. In fact, I also mentioned in the book that I wanted to prove to myself, or try to prove to myself, that cutting back on construction materials will impact the carbon emissions. And after the slowdown back in, was it 2006 and 2007, when you looked at the emissions from concrete manufacturing and steel over in 2008 and 2009 versus the prior, so that was impacted by the slowdown in construction. It was down significantly. There was no question in the United States that that the two were tied together. So you know, if we just stop ordering concrete garden statues, that'll help too. So anyway, I thank you all for joining in, and I hope we can all work together to reduce embodied carbon.
Terrific. Thank you.
Thank you. Right.
Appreciate it.
Thank